Ideal gas equation. You did it in physics. Everyone did physics as a prereq. You did the ideal gas equation. Good. Good. No or yes? Good. Excellent. My question is, what's the mass of the air in the room, right? And that's something that we would use the ideal gas equation to calculate. And we'll get there. And what would happen if we could seal the room, which would be difficult, and increase the temperature by 10 degrees? So what happened to the pressure in the room if we did that? That's our question. Ideal gas equation, PV equals MRT. When or for what substances is this equation invalid? In an open system is the conjecture. Actually, the equation's still valid in an open system, although your mass might change between state points. So yes, your normal use, so to answer this question, sealing the room and changing some properties, yes, it would be a closed system. So if the mass changes from between state 1 and state 2, you need to update it, but it's still valid in an open system. Yeah, go. It's invalid when the substance is not monatomic. No, we still use it. We use it for atmospheric air, even though atmospheric air contains nitrogen and oxygen, carbon dioxide and some other stuff. So no, good thought. Yeah, go.
Change of state.
Where there's a change of state, oof. Yes, but I'm using state to mean something different. So what kind of state do you mean? Liquid to gas, absolutely. Yep, good, and that's along the lines of what you were saying as well. So the steam coming off this, all right, I can't treat that steam as an ideal gas because it's close to its condensation temperature, right? But I can treat atmospheric air, I can treat oxygen and nitrogen as ideal gas because they condense at cryogenic temperatures. So where the temperature or pressure of a system is close to a change of state, then it's not valid. Thank you. This one. So for the ideal gas assumption, which is what you did in physics, and we use it here as well, we'll talk about some modifications to it, but we'll use it here as well. For the ideal gas assumption, we assume there's no intermolecular forces. So we assume that everything's just like spheres and they just bounce off one another, perfectly elastic. No attraction as molecules get close together, which is what they do. They attract to one another. We assume that they all bounce perfectly elastically, and we assume they have no size, which is generally true. So in this room, you could say the oxygen and the nitrogen have very little size compared to the volume of the room. The volume fraction taken up by the atoms is quite small. But for a liquid or a solid, the atoms are butted up next to one another. So it's not true for that. So it's not true for a liquid or a solid, but there must be some transition between when something's a liquid and it's not valid and when it's a gas and it is valid. So we say this works when gases are hot, and that's a high temperature with respect to their boiling temperature, and low pressure. You can pressurize something to the point that this starts to become invalid. And the reason for that is at increased pressure, you've got more atoms in the same space. Your volume fraction of atoms starts to become significant enough that it affects your calculation. Breaks down close to saturation temperatures and pressures. What time are we at?
Almost 20 minutes. 16.
16, we'll keep going until 20. Then I'll turn it off and we'll measure the volume and we'll calculate how long it would have taken to boil. This is the ideal gas law as you've seen it. We'll use this. Anyone seen PV equals NRT, N for Nelly? Yes? We use MRT, M for Mikey, right? And then we just change the universal gas constant to be, or the gas constant we use is the universal gas constant divided by the molar mass of the gas. So we take our 8.3 and we divide it by the molecular mass. So for example, the R of nitrogen gas, so someone writes down 8.3. This is a periodic table of the elements with the things in white being things that are normally gases. Mercury and bromine are liquids at standard pressure and temperature. So if nitrogen has a molecular mass of 14, what's the R value that we would use for it? So we said R equals anyone got a calculator can do that for me? No, it wasn't a hand up. 8dV14 is 7. Yeah, go. Should the molar mass be? Yeah, probably. No. Oh, it's diatomic. Sorry. Nitrogen exists as N2, as we're talking about it. Anyone? 8 divided by 30. Let's see. 0.29. Who was that? Good, thanks for that. Good-o. This is a table from your textbook. Can we call that a bad catch, not a bad throw? But it's on the first row, so it's not a great throw. There's our nitrogen, 28. Well done. And 0.297 nitrogen. So this is a table from the back of your book, table A1. What's special about the substances I've got arrows pointing towards? They are? That's fine. Where do you find octane? Where have you heard the word octane before? Petrol? Yep, good. So octane is a substance that exists in petrol. Octane is normally a liquid at standard pressure and temperature. So is water vapor, well, so is water, H2O. And butane is kind of on the limit. Butane's what you've got in little butane lighters that no one has anymore because no one smokes. So you don't need to compress butane very much for it to become a liquid. So these are examples of where it's risky to use the ideal gas law to do calculations with those things. Where they exist in solution, so assuming it's not condensing too much on the ceiling, all right, the water that is boiling is going into the air and is going into solution with the air, so the molecules are staying in air. That's what this is talking about. So this is talking about water as it exists in a vapor form. So PV equals nRT is what you'll probably learn in physics, and it works. PV equals mRT is what we use, and we use a table to look up the R value rather than remembering it. If we divide both sides by the mass, so we're trying to make things from extensive to intensive, okay, we get specific volume on the left and we drop the M from the right-hand side. So we use that a bit. And we can also take things in a rate sense. So if you've got flow, something changing with time, you can differentiate the volume and the mass with respect to time. So anyone want to guess how much mass is in 2,000 meters cubed? What's the approximate what's the density of air? Sing it out so I can hear it. I've got a boiling kettle close to me. What's the density of air at standard pressure and temperature? 1.2. Well done. Per meters cubed. So 2,000 times 1.2 is about 2.4 tonne. So there's about 2.4 tonne of air in the room, which might surprise you or it might not. If you were going to heat the air up, okay, so my follow-up questions was, what would happen if we sealed the room and increased the temperature by 10 degrees C? If we wanted to seal the room and increase the temperature by 10 degrees C, a question we might ask as engineers is how much energy would that take? And to calculate that, you'd want to know how much mass of air is in the room. Because the more mass of air, the more energy it will take to heat up. How long would that take? So we all generate body heat. Was anyone born after the Matrix came out? Serious question, no. But like next year's cohort might be born, no, because you're not first years, my apologies. I think next year's first years are born after the Matrix came out. I watched it in high school, late high school. My tie-in is people generate heat, and that heat is energy. And the Matrix, and they capture that energy. I don't want to spoil it for you if you haven't seen it. How long would it take to heat the air up in the room is a question we should be able to answer. I realized that I actually just said, hey, what's the density of air? Someone in the room knew it, times it by 2,000. That's not actually using PV equals MRT, which was the point of introducing the question. Thank you, Phil. So I wrote up a solution to that this morning, and that's in your OneNote as well. So using the correct calculation. And the question still stands, how long does it take to heat the room up? And what sorts of things do we need to know? We're going to readdress that when we talk about heat capacity in a later lecture. We won't go there now. But this is a consequence of, so if you say that PV equals MRT, and you have a closed system, so there's no mass exiting the system or entering the system, then you can say that at state 1, you know, P1 V1 equals M, which is a constant now, R, which is a constant, because you've got the same substance, T1, bring the T underneath, and you can say that P1 V1 on T1 equals P2 V2 on T2. So you don't need to do the entire calculation every time. Is that self-evident? Hopefully that's self-evident. And it's useful for if you're working with a closed system, because you can easily say things like, from state 1 to state 2, if you double the temperature without changing the volume, the pressure must also double. If you double the volume without changing the pressure, the temperature must also double. That's the same thing. So there's a relationship between those. And that's where we're going to leave ideal gases for now, although we'll carry it through as a theme throughout the whole session.